All right, so welcome back. So this is the next lecture in section 2, and we're going to start off with some theory here and kind of look at a few parts, and we'll see how it goes. All right, so let's begin with the whole idea of this theory section, and we're going to spend some time on this. We're going to spend a few lectures on it, quite a few lectures on it, is we want to learn fundamentals and definitions, units, things like that, so we all have a vocabulary that we can communicate with. All right, so that's important. One of the big problems with electronics is, like, a lot of times you kind of just, people learn how to hook something up, but they don't really understand what's going on, and so it's unscalable. So you kind of know how to hook up one circuit, but how do you make that into two or four or something else, or more power or less power? So it's important that you understand the fundamentals, and so that's what we're going to be doing. This is going to be the first lecture, and we're just going to start going through this material and learn everything we need to learn. All right, so let's start off. And so I was looking, for a good definition, and the definition that I have here of electronics, the word electronics, is not bad. So let's actually read this. So the word electronics is derived from the word electron, which is the subatomic particle that has negative charge. Thus, electronics is the study of electrons in action, more specifically their properties in electrical circuits. More fundamentally, though, electronics is based on electromagnetic wave theory, which is the study of electromagnetic fields and their respective properties. However, and this is really important, electronics has simplified the field theory into manageable models that can be used to create circuits that perform various functions. All right, so this is super, super important here, and I'm just going to kind of highlight this a little bit here. The idea of electronics is that we would never be able to do anything with electronics if we were to go all the way down to the underlying physics and use, like, Maxwell's equations and atomic theory. It would be incredibly complex. So what's been done with electronics is simplified models have been developed so that we can, under certain circumstances, make certain assumptions, and we can design things and use these parts in a way such that their performance or functionality or the amount of error incurred is tolerable so that we can get things done. All right, and that's what we want. So at the end of the day, we want to be able to use things with simplified models so that we can get work done, so we don't have to go and work with differential equations and Maxwell's equations and down at the atomic physics level. All right, so okay, so that's that. So let's keep that in mind. All right, so let's go and continue on here. All right, so when talking about electronics, let's get rid of this stuff here. When talking about electronics, you're going to hear two different terms. You're going to hear analog electronics and you're going to hear digital electronics. All right, so let's try and differentiate what these two things are. All right, so analog electronics has to do with smoothly varying signals. So signals that can take on any value from, say, one point to another. All right, so from 0 to 10 volts, and we don't know what a volt is yet, but any value in between there, 0 to 10 volts, it could take on. So an analog system is continuous, and it can smoothly vary from kind of one value to another. All right, now you can look up an exact definition, but so the thing to remember is it's smooth, it's continuous, and we have all values. We work with all values in analog electronics. All right, so let's take a look here at some signals that are kind of analog-ish. All right, so so on this little chart right here, we've got some different signals. Now, typically when you see electrical signals, they'll be graphed as a function of time. So the horizontal axis is time, and the vertical axis is something else, typically voltage or current, could be other things, but in this case it's voltage. And we don't even know what voltage or current is yet, right? But for now, it's a magnitude of something. So, we all kind of know 12 volt, 6 volt, 5 volt, things like that. So it's a magnitude of something. All right. Anyway, so if you look at all these waveforms here, so here's a square wave, goes up and down, it has a period, and it has a pattern. All right. Triangle wave, same thing, triangular, sawtooth wave, and then a sine wave here. All right. And then we go down a little bit more, and we have this audio wave, which is kind of all over the place. All right. And so all of these waves could represent, analog signals, all right? But this top wave right here, a square wave, is kind of more digital in nature. So it's 0, then it almost instantaneously changes to 1 volt, and then it's 1 volt for a while, then it instantaneously changes to 0 volts, and so forth. All right, so this is kind of what you'd see in a digital system. But the thing to remember is that everything is analog. There's no such thing as a digital system, ultimately, right? A digital system is a model, all right, that is based on analog electronics, where we use the model in such a way that we look at kind of an extreme case. Things are on, things are off, and the changing from on to off happens so quickly, we don't really pay attention to it. So we'll get into that in a second. But anyway, so analog systems is the basis of everything. All right, but again, analog electronics and analog design is fairly complicated, so we want to simplify that, and that's how digital electronics came about. All right. Okay, so let's move on here a little bit. Let's see what other interesting things we have here. All right, so now when you're doing analog kind of design, very simply, let's just go back in time. Say it's 1950, 1940, 1960. There wasn't any real digital electronics at this point, all right? So when you built electronic systems, you built them out of these simple building blocks, all right? And so there's more than what I have listed here, but these are kind of some of the major ones, all right? So we have resistors. They resist current flow and they drop voltages. Capacitors store electrical charge, all right? Inductors store transfer electromagnetic energy, and capacitors and inductors are kind of opposites. They go together. Diodes, here's our first semiconductor device, allows current to flow only in one direction. All right, and transistors uses amplifiers and switches. These are also semiconductor devices. And then also in transistors, we would have what are called FETs, field effect transistors. Those are kind of the two major players. And then we need power somehow, so we either have current sources or voltage sources, or we have electrical batteries, right, chemical batteries, right, and then we have to connect these things somehow, so we kind of have to have wires or conductors. So with these basic components right here, you can build a lot of things, and this is how things were built, like radios, power supplies, you name it. You can build them out of these kind of basic components, right? A few more, like I said, we don't have them all listed here. All right, so right now let's take a quick look at what some of these things look like, so you can kind of see. Everyone knows what a battery and a wire looks like, but let's take a look at some of these other components just to make sure we know what we're talking about, and see what these things look like a little bit, and we'll talk about a couple things. All right. Okay, so what we're going to do is we're going to start taking a look at things, and I'm going to kind of show them to you, and then we'll kind of zoom into them so you can kind of see. All right, so first, let's start off with resistors. All right, and resistors are pretty simple. So let's get a couple cool resistors here. Just grab a couple random things, and I'm going to show you some different stuff here. All right, and kind of that one's burnt. Okay. All right, so first thing is, so here's a little resistor. All right, so let's put this down here. So here's a resistor here. All right, let's maybe zoom in a little bit here for you. And right about there. Okay. All right, so there's a resistor. There's a resistor. Here's another one. This is a kind of a power resistor. You can see this one's got a little charring on it. That was heated up a little too much. Here's another resistor. All right, see it's getting larger. Again, this is a power resistor. And then here is another resistor, and this is a very large power resistor. Okay, so now let's kind of take a look at these a little bit closer. All right, so if you look here closely, you will see that the resistor itself has some colored lines on it. All right, and if we go ahead and look at these, so in this case right here, this is brown, black, yellow, and then gold. So these lines are used to determine what the value of the resistor are. So, and then this, there's what's called a color code, the resistor color code. So we're going to learn that. Right now we don't need to worry about it, but that's how you read what that resistor is. Now, one thing is this resistor has leads, okay, and see these leads, you can bend them, right? You don't want to bend them too much. All right, if you keep bending that back and forth, that will break. All right, and these have leads because this is called a through-hole component. And the reason it's called through-hole component is because you put it inside of a circuit board, a solderless circuit board, or an actual circuit board, and put it through the holes. So, for example, this is a solderless breadboard, and this is something that we breadboard with, and we're going to be using this. So don't worry about it too much right now. But one thing is, we can put this in here and pop it in like that, and then there it is. And then electrically, these things are tied together in columns, and we can build circuits out of this by adding wires to it. All right, so that's why it's called through hole. Now, another reason also to kind of bring that point home is, let's take a look at, let me grab a circuit here. So here is a printed circuit board. All right, let me back out of this a little bit. So here's a printed circuit board, and just something that that I made for a project or a product. All right, and then you'll notice that there are holes in the board, and those holes are exactly for resistors and components to go into. So for example, if we're lucky, this will go right in here. All right, and so we pop that in there. So, and then we would turn it over, and then we would solder it on this side. Okay, so that's why it's called through hole. That's why it's called a through hole component. And every one of these components kind of has a footprint. This footprint right here is a radial footprint, right? And then you can also see here are some surface mount components, right? In a minute we'll take a look at those, all right? So that's why things are through hole. They go through the holes in the printed circuit board, all right? And some things go on the surface mount, all right? So let's keep looking. Okay, so now we got that resistor, and here's another one, and we'll kind of do a comparison here. So there's the first one we had, and that one's much, much bigger. The reason why they're bigger is the larger one can handle more wattage. All right, so this tiny one is a 1/4 watt, I believe, and this is probably a 1/2 watt resistor. All right, so that means that how much power it can dissipate. Again, we don't really know exactly what a watt is, but we're going to figure it out. All right, and then here's an even bigger one, power resistor, and you can see I even scorched it a little bit right there. So that one's been scorched. All right, and so there's a power resistor. All right, and getting even bigger, take a look here. Here's another one, even bigger power resistor. So these are going to go, you're going to see these in power supplies and things of that nature where you are generating a lot of current and you need resistors in there. All right, and again, we're not quite sure what resistors do. We're going to learn about it. All right, and here's another resistor, and this is another power resistor. And you can read, instead of reading a color code, this is 5 watt and it's 1 ohms. All right, so this is a 1 ohm resistor. All right, I believe this one is 1 ohm. All right, so again, sometimes you have to figure out how to read these things. So this is 5% tolerance. I believe it's 1 ohm, but it could be 10 ohms. Let's check it out. So what do we do? All right, so if we can't read these things and we're not sure about what's going on, then we're going to use a multimeter, and this is one of the pieces of equipment that you need. All right, so let's go take a look, and let's back out here. All right, so this is a multimeter. All right, let's back out a little bit more so you can see it a little bit. All right, so that's a multimeter, and one thing you're going to learn as you start doing electronics is you can never have too much equipment. All right, the more equipment, the better. So a multimeter is a device that can measure voltage, it can measure current, microamperes, milliamperes, amperes, and see this one's so smart, it's saying, hey, when you're in current mode, you need to put the probes in here. All right, it can measure, this one can measure frequency and temperature and sound. It can measure light. So this has a lot of different features. Now this one does not measure, I don't think yet. No, this one actually does. This one actually has a capacitance and it'll check diodes for you. So this is a really cool meter. It's a low-cost meter. In the world of meters, there's a company called Fluke that makes really good equipment, but it's very expensive. And now there's many manufacturers that are low cost that make things just as good. All right, so again, you're going to need a digital multimeter. We're going to talk about this, and you know, like I said, you can just never have enough of these, right? I've got a lot of meters, and each one of them has different properties, and there's more. But, each one has different properties that I like, and sometimes I just need many meters to measure something. All right, so anyway, so let's go ahead and we're going to take a look at this meter right here, and we're going to use this. And then what we're going to do is we're going to measure our guy over here. We're going to measure our resistor. All right, so first what we're going to do is we're going to turn this on, ohms. All right, and that's what resistors are measured in ohms. All right, that's their impedance. And again, we're going to learn about that. All right, and meters have different scales, and so this is an auto scaling meter. So what's going to happen is you can see that it says auto up here, and it's going to try and scan the component at different value ranges until it kind of locks into the range, and then it'll drill down and figure out what the actual value is. All right, so let's just do a quick check here. So how we do this is we just basically take the probes, all right, and we put the probes over the component, and now we actually are impedance as well, but a human being's about 100 to 200 kiloohms, so as long as the resistor is much smaller, we won't notice that too much, or just try not to touch it too much. All right, so we touch it on there. All right, we touch both leads, and it's tracking, and it's figuring out, so it says 0.470 K, or 470 ohms. All right, so 0.47 K ohms or 470 ohms. Okay, so that's 470 ohms. Great. Now let's come over and we're going to get this big guy. All right, and we believe that this is 1 ohm, I believe, but it might be 10. So we're going to put it on the two leads there, and we're going to see what it does. And it looks like it's 1 ohm. All right, so that's correct. So it's 1 ohm, not 10. But again, if you don't know how to read these things, just get out your meter and check it. All right, so that's 1 ohm. All right, and you'll notice that it's not exactly accurate. So we've got all these decimal places here. So now we can kind of change the range now that we know what we're dealing with. And now I'm going to put it into just ohms. And now it's getting more accurate here. So it says it's 1.1 ohms. All right, now these devices to measure this, it runs a current through it, and then it senses the voltage through the same cables. And this is a little bit inaccurate. So when you start getting down to very small values, it's harder to measure them. So you have better and better meters that cost more and more money. All right, and there's different ways to do that, but we'll talk about that later. We don't really care about it right now. Okay, so we turn our meter off. All right, so let's keep going. So the next component that we want to talk about is, let's see, let's talk about capacitors and take a look at some of those. All right, so let's come back down in here. All right. Okay, so let's bring out some capacitors and see what we got here. So first, there are many different kinds of capacitors, and there are some that you've probably seen quite a bit of. All right, and I'm going to show you a lot of things, a lot of way that I do things. Okay, so you see I've got this little bin here. Electronic components are really small, and you will lose them. So see here, this is like my 22 picofarad, 47 picofarad, 100 picofarad, all right? And these are ceramic capacitors. And then here's some other ones. And so there's different ways of keeping them, but these things are small and you will lose them, all right? So different kinds, these are all ceramic capacitors right here, all right? So let's take a closer look at one of these, all right? So I'm gonna let me grab a little blue one, and I'll grab a little orange one. All right, and let's go over to the zoomed camera. Let's take a look. Okay, so in this case, so this is a ceramic capacitor, and you can see it says 101. All right, so this is the value of it, and I'll show you how to read these later. But this is usually measured in picofarads, and so it's 1, 0, and then the last digit is a multiplier. But again, sometimes these things have different kinds of encoding, so you gotta make sure you're reading it right, and different vendors do different things, and you can always get your meter out and check it. So this is a ceramic capacitor, and it's not polarized, so it can go in a circuit either way, and it has certain properties. And ceramic capacitors are probably the most widely used now. Before it used to be electrolytics, which I'll show you in a second. And here's another ceramic capacitor. And again, this one, let's see if we can get on there. Yeah. So that one again is, that's the same value. That's the same value as the one we were just looking at, the orange one. And yeah, 101. Yeah. But you can see it's a little bit smaller. So there's a couple reasons for that. So one is the materials that it's made out of might be slightly different, and then also the voltage that it can withstand may be different. So a large capacitor typically will be able to withstand a larger voltage than the smaller capacitor. And we're going to learn about capacitors and what that even means, all right? So, okay, so we got those two right there. Okay, let's keep going and see what else cool stuff we can find here. All right, now back here, we've got all these capacitors, and this is kind of a little grab bag. So as I'm building things and as you're building things, you got to figure out different ways to hold things. So kind of here I put my electrolytic capacitors. So electrolytic capacitors, let's take a look at some of these. So let's just get some colorful ones here. And electronics is also fun because it's a lot of color. All right, so here are some. So let's take a look at these and see what we kind of got here. All right, so let's bring them over. And so the first thing that we notice is the leads are coming out from the bottom here, all right? And so one thing is these leads are bent right now, and I don't like bent leads. So one thing I want you to get comfortable with is kind of using tools and messing with things and kind of fixing things up. So see, I just got these little diagonal pliers, and I'm just kind of straightening that out. See that? Now I'm happy. All right, so that's pretty. All right, so let's take a look at this. So this is an electrolytic capacitor. And so a couple things. First, you see this electrolytic means it's polarized. So it has a plus and a minus, and it works in that direction. If you don't put it in that direction in your circuit, it'll explode or not function or do bad things. All right, next, it has this negative here. That means this is the negative side, and the other side must be the positive side. All right, now you'll see a couple other things here. It's got a value 150 microfarads. Again, we don't really know much about capacitors yet, but we're going to learn they're measured in farads, and they're usually measured in micro because a farad is huge. All right, 150 microfarads, and then usually right next to it is the voltage that it can withstand, and this one can withstand 10 volts, so it's a 10 volts, 150 microfarad, and then the other writing is the manufacturer on there. All right, now this is called a radial capacitor, and the reason why it's radial is because the leads are out here radially. All right, and so if we have a circuit board like this one, put this one in here, and we can see where this guy could go in a place like that, and I just put it in wrong, right? So a capacitor goes there, but you can see there's a plus there. I actually put a plus to remind myself that's the plus side, so the other side's minus. So when I actually manufacture or assemble this, I would put that in there like that, and then I would solder it together like that. Okay, so that's radial. All right, now let's take a couple other ones here. So here is another one, and this one is 35 volt, 47 microfarad. All right, so this one's a much higher voltage, right? 35 volts it can withstand, and it's 47 microfarad. And the other one we had, no, excuse me, this one, yeah, this one was 10 volts. This is 150 microfarad. So they're roughly the same size, but they swap capacitance for voltage in those two. All right, so let's take a look at another one, kind of a bigger one. And take a look at this one right here. So this one's interesting. So this is 250 volts. This is a capacitor that might be used in a high voltage circuit, right? 250 volts is very high voltage. So this might be in a power supply, AC/DC power supply, and where you need this high voltage tolerance. And this is 47 microfarads, all right? Again, it's radial, all right? And let's see. Here's another kind of littler one, little tiny one. And again, this one is 100 volts, and but only 1 microfarad. All right. And again, you know, these leads, they kind of get, you know, wound up and messed up. Just kind of bend them back in place. All right. So there are some of those capacitors right there. Now let's take a look. There's another kind of capacitor, and there's many kinds of capacitors, countless capacitors. These are called tantalum capacitors. All right. So let me show you this. These are tantalum capacitors, and tantalum capacitors are also polarized, and you can see the little pluses. So if you look here carefully, you can see, get a little tip here, right there is the plus, the other side is the minus. And you can see there's 35 on here. These are 35 volts, right? And then you can see the value is 106. 105, 105. These are actually 1 microfarad. When you do the math and do the little encoding, it's 1 microfarad. All right, but I'll show you how to do that. So these are dipped in resin, and these are really good in power supplies. You're going to see these in a lot of power supplies on the inputs and outputs, and they have good properties for that. But these have kind of been overran by ceramic capacitors as well. Because they're low cost. All right. So anyway, so those are tantalum. And now, so what is this? So this is a tape, and this is kind of how these things come. So again, these are through hole, and so see, these are cut. So I cut these off. So now, if this was a manufacturer, a robot, this tape would be loaded into a machine, and it's usually on a big reel. And then the machine sits and comes across and it grabs these and cuts them, and then inserts them into the circuit board. All right. So those are tantalum capacitors. All right, and again, those come in all kinds of different sizes and shapes, and sometimes they have writing on them, sometimes they don't. So let's take a look. Here are a couple others. All right, and there's another little tantalum capacitor, and this one I believe doesn't have anything on it. Nothing, no writing on that. So if you do not know what the value of this thing is, you are in trouble. So you're going to have to use a capacitance meter, or you're going to have to put it in a circuit, and you could maybe calculate what the capacitance is if you really wanted to. Here's another one, this little orange one. These are kind of cool. And so this one is 5 volt. There's the plus side, and the minus side must be the other one. And this is actually 1 microfarad. You can see that little one right there. And again, they give you, there's no love here when they put the values on these things. If you don't know what it is, sometimes you are in trouble. All right. So anyway, let's take a look. Let's grab our meter again. Let's grab our meter, and let's see if we can measure the value of this one. Okay. All right. So we're back over here. Okay, so we're back over here to the main area, main screen. So let's go grab a meter that can measure capacitance. All right, and let's see what we can come up with here. All right, so let's get this one. So this one has a capacitance checking function, or measurement function. All right, so let's turn this on, and if we look around here and we look around at this dial, right here is the capacitance measurement. And so all we need to do is put it on that right there. So turn it on. All right, so our meter is on, and see it's measuring now in nanofarads. And again, on meters, and we're going to go over this, we have a range button here. And if I press this range button, it's going to start changing. So we're kind of giving it an idea where we think this thing is. So microfarads, tens of microfarads, right? So I think this thing is probably a microfarad or so. So let's put it on that range right there. Okay. And then what we're going to do is we're going to, let's just back out a second so you can make sure you're seeing everything here. And then the leads are just in here. And we're just going to grab these leads. All right. And here are our leads. So we're going to come back here so you can see the screen a little bit better. And we're going to take our capacitor here. And now, when we're measuring this, we also kind of, if it's a polarized capacitor, we want to measure it in the correct way. So I can see that the lead on the right is the positive lead, so I'm going to bend those out. Now again, I have a lot of capacitance in my skin and so forth, so we want to try to kind of hold one of these on and then just kind of touch the other one. All right, so let's give that a try. So we're going to touch this on here. All right, and sure enough, it says 1.1 microfarad, and we believe that this is about 1 microfarad. So this is correct. Now, the one thing about these different capacitors and these different kinds of technologies, whether it's ceramic, electrolytic, whether it's tantalum, and there's all kinds, polystyrene, there's mylar, the list goes on and on. There are quite a few. You can Google it and look at it. They all have certain tolerances. Maybe the tolerance is 5%, maybe it's 10%, maybe it's 20%. So this one right here is probably 20%, 10%, and that's why we got that 1.1. So that's completely fine and tolerable, and we're happy with that. All right. So, okay, so that's the end of that one right there. So we're going to take our meter, turn it off. A lot of meters have auto off functionality, but it doesn't hurt to turn it off so that you kind of save those batteries. Okay, so, all right, let's continue on and look at some of the other components. All right, so what else do we have in our little list here? So we've got resistors, capacitors. Okay, so let's take a look at inductors. So what is an inductor? So an inductor is a device that is basically nothing more than a coil of wire. All right, so let's take a look at some of these. So let's come in here and let's zoom in. right. I think we can get away with about that before this thing freaks out on us. Okay, so here, transistor got in there. All right, so these are all inductors. And where's our other inductors here? Here, we got this, and we got this. Oh, and just to show you how big, I just wanted to show you this. Back to our capacitors. Here's another capacitor. Look how big that is. So what is this? 25 volts and 4,700 microfarads. Look at that. That's cool. And then here's another one. So these are ripped out of power supplies. So I'll tell you one thing. Most electronics are kind of useless to rip apart devices and take them. But these big capacitors are useful if you need big capacitors because they're fairly expensive. I mean, it's made out of matter, right? So you got to pay for it. So these are big capacitors. So you can grab these out of an old power supply or something. If they're still good, definitely take them, desolder them, and keep them. And then, and then real quick, here is another. This is a AC capacitor. This is called an XY capacitor. And so this is used in AC circuits. So this can withstand AC, very high voltage, and it's usually very small capacitance. So this is like 0.47 microfarads and 250 volts. So that's an AC capacitor. All right. And then before we move on, this is a precision resistor. And actually, let me show it to you over here on the zoomed in. So this is a precision resistor. So this is only 0.01 ohms, right? Now, why on earth would you want a 0.01 ohm resistor, right? Well, that's usually to current sense. So in a circuit, there'll be a current flowing through some part of your circuit. And you put this teeny tiny resistor in here. It'll have no effect on the circuit, but it'll generate a small voltage, and then we can sense that voltage with an analog digital converter, and then we can compute how much current is flowing through the circuit. So we don't really know about voltage and current and all that, but that's kind of what these are for. So this is 0.01 ohm, and it's 1%. That's very, very accurate, and it can handle 3 watts. So this thing can dissipate a lot of power. All right, so that's that. Okay, so let's come back to our inductors here, since they have the floor. So all inductors are coils of wire. All right, so you take wire, you coil it up, and you've got an inductor. If you wrap it around something that has magnetic properties like iron or ferrite, then it'll have more inductance. Okay, so we've got 3 of them right here, and then let me show you. So here's kind of what's going on the inside right there. So there's other inductor, and this is inside of this is actually ferrite. It's actually iron. All right, and then I wanted to show you this because I just kind of want to show you how things come. So when you buy these parts, all right, so this is from DigiKey, and so it says choke, that just means inductor, 68 microhenries, 20%, and it's made out of ferrite. So you're going to have bag after bag, box after box, you're going to have countless little parts, all right? So it's important to, keep things organized, or you will go nuts, like actually crazy. Okay, so let's take this out. And let's go ahead and let's look at it. Let's look at these all zoomed in so you can kind of see what we have. All right. So this right here. So this is an inductor. So this is pretty cool. So now the first thing is the center of this is made out of iron or ferrite. Okay, powdered iron. And it has certain magnetic properties that increase the flux linkage and make this a better inductor. And then you can see the wire comes in here, the lead, and then it's going to this wire here, and it's wrapped around here so many times. So the inductance is proportional to how many wraps, how many turns. It has something to do with the material also, the ferrite, how many turns, the diameter of the turns, and then the diameter, the thickness of the wire, how much current can flow through it. So all these things have to do with how you compute the inductance. All right, but now this is kind of weird. So this wire is just touching each other, right? It looks like it's shorting. Actually, it's painted, or it has a kind of a tarnish on it. So there's a coating on here, and that protects the wire. So that, and the reason why we do that is we want to wrap these things as tight as possible, so there's no insulation other than a thin coating. And maybe that coating is, a couple thousandths of an inch thick, all right, and or a thousandth or even less thick, and that protects it so there's no shorting. But you can get more coils in the same amount of space, because if you have insulation on the wire, then you're not going to be able to do that. All right. So again, this is this right here is an inductor, and we can see what's going on here. All right. So and this one's called, and this component we talked about radial. This one's axial, right? So it's axial because it goes on an axis. All right. So that's a pretty big inductor right there, right? Okay. Here's another inductor. And this is the exact same on the inside. So if I were to pull off, this is rubber sheathing on here. If I were to pull this off, you would see this thing is wrapped in here. All right, and there you can see we've got our two leads, and you can actually see the wires going from the leads, a little wire right there in that corner. All right, and then if you read this again, these things have all kinds of different encodings, and but this one is probably 2 something, right? And what this means in this case, it's 2 are the first two digits, and then this is 10 to the 1, or times 10. So this is 220 microhenries, I believe. Not 22 microhenries, I believe it's 220 microhenries. Again, if you forget how to read them or you haven't played with them in a while, you just get your meter out. That if you have an inductance meter, and then you just measure it, okay? But the values are on there some way, and sometimes there's no value on there, all right? Okay, so there's that. Now here's another one. This is another inductor, and this is called a ferrite bead. And you can see we just got ferrite, this material, and then we just got a few turns in here, and then this goes in a circuit. And these are typically to reduce noise, right? Because inductors have certain properties to signals, and they like blocking high frequencies. So this is good to block high frequency noise. So there's one right there, and then here's another one, even smaller. Right, and it just goes just so right here in this one little area, this is going to be more inductive because of this ferrite. All right, and there's going to be flux linkage, and so you're going to get a stronger inductor even though it's just one wire. So every wire has inductance. So every time a current flows through a wire, magnetic field is generated. All right, and so but when you put this ferrite on it, it changes the properties of that. All right, so again, that's axial, and let's see. I think that's about it of those. So we've looked at a number of devices that were all through hole. So everything so far is kind of through hole. All right. Let's take a quick look here at something that is not through hole, something that is kind of surface mount. So again, when we look at, so let's take a look at, let me show you this little circuit here. So here's just a little power supply I did. And you can see we've got all these components and these little weird little rectangular solids. These are all surface mount devices. So, you know, here's a capacitor. These are resistors. Here's an integrated circuit. There's an inductor. That's actually an inductor. And there are also some through-hole parts. So what's through-hole? So this is through-hole, this little terminal block, this little switch, and see, and basically there's holes drilled through here, and they're soldered on the other sides. Okay, so this is what a surface mount inductor might look like, right? And here's what a surface mount resistor. So you see they're tiny, and they get very, very, very tiny. They get so tiny, in fact, it's very hard to work with them because you will lose them. All right, so for example, let's go back over to the big screen here. Let me show you this. Let me back out of this for a second just to show you. So all right, so when you start doing electronics, you're going to need to store them somehow. So this is just a little case. Let me back up a little bit more so you can see it maybe. All right, so this is just a little case that holds the components. All right, and so what is in here? Uh-oh, wow. So yeah, believe it or not, I sat and all these components, let me zoom in a little bit for you. All of these components I took from little holders, little packages, and then I took them out, and then I put them inside of all these little boxes. So if I open up one of these little boxes, the little components will be inside of here. And I want to show you just how ridiculously small these things are, okay? Ridiculously small. So in surface mount technology, there's a number of different size delineations, and the numbers have to do with the dimensions in millimeters. Anyway, the sizes kind of you're going to see use most are 805 and 603. 805 and 603. Then it goes down to 402, and then it goes down to 201. So 402 is at the point that most people can't with their eyes even work with them. So most people will work with 805 or 603. And again, we'll look at that more when we get to it. Once you get to 402, they're just too small. Then there's 201, which are ridiculously small, and then there's even 100 series that are even smaller than that. So let's grab, just to show you how nuts this is, and we'll use the tip of a pen to kind of give you some reference. So let's grab an 805. So if we look around here, let's see what we got here. So here is a, let's find something good that's 805. All right, so here's a 4.7K 805 resistor, all right? And you can only write down so much here. So there was probably a tolerance in the type of material it was made out of and all that. But anyway, I'm going to open this up, okay? And I'm going to grab one of these out. And this is just ridiculous how small these are. All right, I'm going to put it on the tip of my finger, all right, which you cannot see very good. Now I'm going to move over to the zoomed in camera. Okay, and there it is. Okay, so that is the teeny tiny little part. And let me grab it again with the tweezers. All right, this is not easy to do with this camera. All right, so there it is with the tweezers. Let me back it out. Okay, so look at that, and there's that giant tip of a pen. So this is, you can see the number on there, 472, and let me get it back and zoom. So it's 4.7 times 100, so that's 4,700, right? And that's the 2 is again the multiplier. So the smaller they get, they have no writing, and so if you lose it, you have no idea what the value is anymore. Okay, so if you lose the packaging or you forget what the value is, you have to measure it. All right, and again, how do you measure something like this? Well, just like we did the other thing, you just and here's another thing. When you're dealing with things this small, stiction and different physics properties wonderfully come into play, and so you're like working on something, and then you're like, where's the surface mount component? Well, it probably stuck to you, and now it's on the floor, on the carpet, and you will never find it. So if I want to measure what that value is, right? So oops, if I want to measure what that value is, let me zoom in a little bit. Let me see if I can get it to cooperate a little bit. Oh, that's not bad. And I'm going to turn it around. Okay, turn it around. Okay, crazy, crazy. Okay, so now let's get one of our meters. And I'm going to get a meter that has sharp probes. All right, and let me see. I think this one's sort of got sharp probes. Okay, all right. So now what I'm going to do is I'm going to close up the surface mount components, and we'll put our meter over here, and we're going to kind of go back and forth. So we're going to set our meter, so it's 4.7K is the value, so we'll put it on 20 kilo ohms range. And again, we really don't know what an ohm is and all that, but just bear with me. All right, so we've got that, so we got our meter, and now we're going to come over here, and so I have 20/20 vision still, and this stuff is impossible to see. So right now, when I work with surface mount electronics, I wear magnifying lens glasses, and so that these will really help you. So this kind of stuff you can wear, and you can just get these at a store, or if you want to get crazy and steampunk, I wear these kind of things, and they have lights on them and stuff. So those are really cool. And these are super magnifying glasses, so those are really cool. All right. Okay, so let's try and put these probes up here, and let's see if we get 4.7K. All right, so it says 4.7K. It looks like 4.7K, so let's see what we got. So we put it up there, and ever so gently, and then watch the meter, and 4.68, yep. And this is probably a 5% resistor, so it's within tolerance. And again, there you go. Very nice. And that's how you do it. So if the number's on there, great. Okay, so you can read that. Now, let's assume that we want to go smaller. Okay, we want to go smaller than that. So we're going to put this back. So we're going to go back to our surface mount case here. We're going to open this back up. We're going to find the 4.7. There it is right there. We're going to put that back in there. Make sure it's off our finger. Okay, and now let's see if we can find something else. Let's punish ourselves even more here. So let's find something even smaller. So let's find a 603 size, even smaller, and something. Let's look at a capacitor. So we'll find a 603 capacitor. So a really common capacitor is, let me see if I got it on screen here. Yeah. So see this 0.01 microfarad? Let me see, do I have any in there? Yeah. So 0.01 microfarad is a really common capacitor used in circuits that we use a lot. So let's grab one of these. So we're going to open this up, all right, and I'm going to go in here and grab one of these. And this is even ridiculously more small. Okay. So there it is there. And you cannot even remotely see that. So now let's put it under here. All right. And there it is. And I'm gonna zoom out a little bit here. Okay. Okay, so there it is. So now again, let me show you the tip of the pen to give you some scale. So, and so this is just horrible. And then when you're building something, let me get you another little circuit board here. Okay, so here's another little circuit board, and this is all surface mount. So this is a little charger that I designed, a little USB lithium-ion battery charger. So now, looking at this, here's the capacitor C2, and this probably takes a 603 size footprint. So you can see we just put it right on there. And so you would place it right on there. All right. and one way or another, you need to solder that on there. Okay, that's why when we're doing electronics, a lot of times we'll start off and do through holes design only, so that we don't have this problem, because this is really hard to do. All right, and but there are different ways to do this. All right, so let's take that, and usually you just kind of, it'll stick to your finger because of moisture. So we'll take that and we're going to put that back. All right, so let's go back over here and hopefully we can find it. Here it is here. Put that in there. Now, have I ever dropped this? Yes, but these things all close pretty good, and I keep this thing closed. But I can't. If you lost all these and they got on the ground, you would never get them back together. Okay. Now, let's go back and we got a couple more things, but I want to show you something else. So here is this board is completely through hole, completely through hole. All right, so you can see that. And let me zoom just a little bit here. And let me turn that around. So this is a through hole so that people can build this, and so you put all these parts in here and you solder them. So, but typically most people, well, I don't think anyone's made a professional product in decades that is not completely surface mount. Everything is surface mount now. Everything is surface mount. They'll have some mechanical components that'll be through hole, but you have to do it. And look at these chips, right? Look how fine those are. Let's go to the small. Yeah. So you can see that's no fun there. All right, so that's a processor, another processor. You can see how small everything is, right? So robots build this stuff, but you can build it too. I build stuff this size all the time, not a problem. Here's another board. Again, this is all surface mount except for the through-hole components because they need to be mechanical to plug into something. Okay. Okay. So what else we got? Diodes and transistors. Okay, last two things. Last two things. Okay, so let's take a look. So here is a transistor. All right, let me zoom in a little bit on this one. Let's see if we can get in here a little bit. Okay, so there's a transistor, and we'll go real close to that in a second. All right, and a transistor is an amplifier. And again, how do they come? So these are through hole, so they're going to come in this kind of tape, and they'll be removed from the tape by a machine and then inserted into the circuit board. All right, so if we go look closely at this, let's go over to the other screen here. We can look at this, and if I get the light just right, you can see, so it says PN222A. All right, so this is actually a NPN transistor, and we'll learn what the N's and the P's mean later. And a transistor has three leads, a collector, a base, and an emitter, or emitter, base, and a collector, depending which way it goes. And again, which way does it go? You have to look up the specific manufacturer. It may go one way, it may go the other. All right. So that's that. And again, you have some idea of scale. All right. So that's a transistor. Now let's move over and let's look at a diode. So let's look at a diode now. So there's a diode on the big one. So there's a diode there. Here's another diode here. And then diodes can get very big. So diodes are semiconductor devices, and they allow current to flow in one direction. All right. So let's take a look at what these things look like up close. So come up here, and again, let's see if we can get the right kind of lighting here. It's always a little bit hard. All right. So it's very specular, but if you look at this, it says 1N4001. This is a very common, famous diode, the 1N4001. All right, and this is a silicon diode, and allows current to flow in one direction. Conventional current, which we're going to learn about, will flow from this side. This is the anode, and this is the cathode. And the cathode always has this stripe on it, this white stripe usually. Conventional current will flow from left to right here. All right, electron current flows from right to left, but we're not going to talk about electron current when we actually do things. But we'll figure what that means in a while. And here's another diode. So this one is called a glass passivated diode. Let me bend those up a little bit, clean those up. All right, and again, you can look on it, you can see the number on it, which even under this magnification is difficult to see. But anyway, the cathode is to the right. You can see the black bar. So again, current is going to flow that way. All right, and these have slightly different properties, and the value has to do, the part number has to do with how much current can flow, depending on the manufacturer and voltage, things like this. So and sometimes the part numbers are just completely random. All right, so anyway, those are a couple diodes, and that's what diodes look like. Again, these are axial diodes. and you can bend these leads. Got to be very careful. A lot of these are made out of an aluminum alloy, and you bend them a few times, they're done. They're not meant to be bent. They're meant to be bent one time and then inserted into a circuit board. So if you're going to use these and you're going to put them into your solderless circuit board and work with them and all that, you have to be careful, right? So again, we can zoom out here, zoom out a little bit, and we'll bring our solderless circuit board, which we're going to learn about this shortly. But again, we're just going to kind of jump into it. And so what I'm going to do here is I'm going to take this and I'm going to bend it right at that joint. Do it like I mean it. Don't, just kind of do it a little bit. Just do it, get it done with. Now, another thing you're going to notice, the ends are blunt, and they're going to make mechanical contact. There's little clips inside of here. So these wires are common like this. These clips allow current to flow in these columns. So if you put it here, this is all connected, right? If you look at these closely, they're little clips, and when you push something in there blunt, it's going to catch it, all right? So what you typically do is you might even take some sandpaper or a file and file these down a little bit and kind of make them, kind of chamfer them, and they'll go in a little bit better. So I'm going to put this one, I'm just going to put it right in here. And again, do it like you mean it. So I'm pushing it not too hard, kind of wiggle it, kind of, roll it around, gotta, kind of work it in, and it's not very easy. So like right there, it's really binding, right? So not making me happy, and I'm probably messing the board up a little bit. And again, I'll do it here, trying to get the camera angle so you can see it. And oh, see, it bent. So right now, this is telling me, hey, you need to really chamfer these a little bit and clean these ends up so you can kind of push them in here, not damage this board. Because what you're going to do is, when we're building things, we're going to take wires, all right, and let's find a little wire here to kind of show you. We're going to take wires, and we're going to plug these wires in to this board, and we're going to connect things, right? So like say we wanted to connect those 2 points. That went in really easily, right? So, but if I open these things up by putting parts that don't fit, right, then I'm going to damage this board over time. So that's why if you want to put these in here, you're going to have to chamfer these and get a little file. A little nail file works really good, that kind of thing, or a little bit of sandpaper, and just take the sandpaper and put it down and just go like that, go like that, all right? Real world stuff, all right? But we're going to get to that when we get to that more. Okay, so what else do we have? What else do we have here? So we did transistors, we got batteries and wires. We already know what those things are, so don't need to worry about that. All right, so I think we've done about enough. And in the next lecture, we're going to do digital electronics, and we're going to talk about some other things so that we have vocabulary to talk about electronics. And we're going to start, getting a little bit into more of the theory now that we've kind of had kind of a hands-on section here, and we kind of see things and see what things look like. All right, so I'll see you in the next lecture, and that's it.